So, hi everyone. So for today's class, we will be covering the rest of the remaining topics. That is on first we'll discuss on Boltzmann-Einstein statistics. Then we'll be discuss on Maxwell-Boltzmann statistics. So these are the two remaining topics, and also we will discuss some relevant problems regarding these two topics. So before doing that, let me just revise the things that we missed from our last discussions. Okay. So, so, in our last class, we have mostly discussed about how, from basically in a reaction, uh, by calculating the energy difference, the difference in the 0 point energy between the products and reactants of a reaction, and by calculating the distribution of energy of both reactant and product molecules, you can basically calculate the partition function, and from there basically you can calculate the equilibrium constant of a reaction, right? So let me just write it once again. So let's suppose a reaction is happening like this. So reactants and this is the product, both are in equilibrium, and let's suppose the reactant number of reactant molecules in R is equal to summation over reactants e to the power minus beta ei, and similarly products would be summation over products e to the power minus beta ei. Now from here the equilibrium constant K for this reaction can be written like this: K equal to ratio of NP by NR, or we can basically write this NP and NR like this. So NR we can write it, we have actually proved this thing, N by Q into QR. QR is basically the partition function for the reactants, molecular partition function for the reactants. Similarly for products, N by Q, QP. By Q, QP into e to the power minus beta delta is 0. So what is delta is 0? So basically the products and reactant molecules are basically distributed like this. So let's suppose this is the energy distribution for reactant. So here these are energy distributed. And for products molecule, the distribution starts, the 0 point energy distribution starts from a higher level compared to the ground state. So the for product, the distribution starts like this. This is for the reactants and this is for the products. And this is the difference between their 0 point energy levels. Okay. Now, for this kind of a system, equilibrium constant K, Np by Nr equal to Qp by Qr into e to the power minus beta delta N. Okay, this is the expression for the equilibrium constant K for this sort of a reaction. Okay. Uh, mhm. Now we have also shown, let's suppose for there is only one energy level for reactant molecule is there, and the other energy level of product molecules are equally distributed like this, and their energy difference is delta E 0. Now for this kind of a problem, we have calculated the value for equilibrium constant K. Looks like the K equal to Kt by epsilon. Epsilon is basically the energy difference between each of the energy levels for the product. This is product, this is reactant. So reactant has only one energy level, and product has many energy levels, but their energy levels are equally spaced. Okay, and the difference between their energy level is epsilon. So for this case, equilibrium constant K is simply given by K equal to Kt by epsilon into e to the power minus delta E 0 by Kt, RT, sorry. This is the expression of the equilibrium constant for this system. Now, uh, so this is a very important quantity, because if we know these things, basically the reason for in order to calculate this equilibrium constant is this equilibrium constant delta G is directly related with, I mean, change in delta G for every reaction is directly related with the natural law of the equilibrium constant K. So if you can calculate this equilibrium constant K, you can basically calculate the change in the Gibbs free energy for that reaction. And if you know the change in Gibbs free energy, you know that change in Gibbs free energy also depends upon change in Helmholtz free energy and change in entropy. So if you know the change in Gibbs free energy, that quantity also gives you the measurement of change in enthalpy and also the change in entropy. So that means that somewhere the change in enthalpy and entropy are also can be related to the equilibrium constant K. But that's why by calculating this quantity, you can basically measure many of the important thermodynamic quantities of a system, of a reaction system that is obviously in equilibrium. Next what we have done, we have basically solved some problems regarding to that, this kind of a system, where let's suppose we have been calculated, let's suppose there is a gas carbon monoxide. So its vibrational wave number is given, the temperature is given. So from that case, we have calculated the specific heat problem. So which type of problems we have done? Okay. Okay. So now, today, for our today's discussion, we will be first discuss about how to calculate the equation of state for a canonical system. Okay. So let me first write the canonical partition function is basically denoted by Q N V T, right? So that means that this canonical part, this is canonical partition function, means the partition function for the whole system that includes basically the partition function that comes from the individual molecules. Okay. So this whole canonical partition function or ensemble partition function is basically a function of volume, the number of particles or number of molecules, and the temperature of the system. Okay. Now, if you somehow got the expression of the canonical partition function of a system, from there itself you can calculate the pressure, right? We have already established this thermodynamic relation, right, where the pressure is related to the partition function Q. The equation of the relation is simply written by P equal to KT into log del V of ln Q. This is basically, and this equation is known as equation of state. Okay. This equation is basically known as the equation of state. So for in general any kind of a system, this is a very general equation. It's not a specific application type of a equation. It's not like this. It's a very general equation. So whatever the system you have, if you can able to calculate or get the expression of its canonical partition function from after getting it by putting that partition function expression into this equation or this relation, basically gives you the equation of state for that particular system. Okay. So by evaluating this equation basically gives you how the pressure would be a function of number of particles, volume, and temperature, right? So we know that for a perfect gas, how this equation basically looks like. So for perfect gas, the equation of state looks like this: PV equal to NO3. We all know this basically. Okay. Okay. So let's do this. Let's prove this. How this from this relation for an ideal gas type system. If you know the partition function, let's check how we are getting this beautiful relation PV equal to NO3. Right? So for that, let's first consider. Let's first write the equation once again here. So the relation looks like this: P equal to Pt into delta of ln Q by delta V at constant temperature. Okay. Now here the canonical partition function Q, if suppose the system consists of n number of indistinguishable particles and or indistinguishable molecules, and The partition function for each, the molecular partition function is basically denoted by small q, molecular partition function. And for, so that means the total ensemble canonical partition function q can be written in terms of small q, and the relation looks like this for indistinguishable particles: q to the power n by n factorial, right? So now what we have to do, we have to uh, just substitute this expression of the q into this expression of p, and after doing that, we can write it like this: p equal to kt into delta of del b into ln q to the power n by n factorial, right? Now if we do further simplifications, it looks like del b of, so ln q basically looks like this. So the first term will be ln qn, then minus ln n factorial. So basically I basically decompose the multiplication, sorry, the division into subtraction by using the property of log. Now p equal to kt into n into ln q minus, so we are using the Stirling approximation here, minus n. Okay, now equal to kt into n ln q minus n ln n plus n. Okay. So there is also del v is there. Okay, forgot to write it. So here, as you can see, so inside the derivative, if you observe the things carefully, these two are the simply constant terms, right? So doing the derivative with respect to the volume for these two terms basically gives you 0. The only terms that is dependent on the volume is this molecular partition function q, right? Because you know, if let's suppose we are considering simply molecules that are translated, that only has translational degrees of freedom, for a time being we are not including the vibrational or the rotational effects here. So if the molecules only has translation, so we can write the q, the molecular partition function, is equal to qt. Translational terms are only involved here, which is basically v by lambda q, right? So lambda is the thermal wavelength, and this expression is given by lambda equal to h by 2 pi m kt, right? After putting the lambda here into the expression of the molecular partition function, so inside the derivative with respect to the volume, this first term only survives as it's a function of volume, right? So just write this thing, n into ln of q. Took the derivative, so derivative with respect to the volume gives you n into, so there's a cube term, so 2 pi m kt to the power 3 by 2. Now if you do the volume derivative with respect to the volume of q, that gives you 2 pi m kt by 3 by 2. The whole thing is divided by h cube. Okay. So now cut out the common terms. So this will cancel. This cancel. So only terms. So there's a b term will be there. Yeah. The b term would be there. So the b would be go to the left hand side. So pv equal to nkt. Now here n, you can write it like this: number of moles into the Avogadro number Na. So n into Na into k. K here is the Boltzmann constant, right? we know the real gas constant R is equal to Na into K. So just substitute this thing here. So this gives you PV equal to the infamous relation PV equal to nRT. Okay, so this is how basically. So basically, what we have done here, we for a simplistic ideal gas, the perfect gas, simplistic perfect gas, by using this relation, that what we actually what is actually known as the equation of state for any general kind of a gas system, we have derived the relation PV equal to nRT, right? So for that, we consider the partition function Q of that perfect gas is equal to this Q equal to Q translation. So we'll only include the translational terms here. So that is the V by lambda. V is the area, the volume where the gas is moving, the gas is contained basically, and lambda is a thermal wavelength that is associated with the gas molecule. So we put up the whole. So we basically substitute the whole expression into this the expression of Q. As we know, Q for indistinguishable particles, Q are related to the molecular partition function small q using this relation. So we are just after substituting, we take the log, then you do the derivative. The only terms is this that will survive against the derivative. After doing the derivative, we are getting PV equal to NKT. From there, R equal to Na into K reduced, which gives the final relation, that is PV equal to nRT, right? Okay. So, uh, so here for the ideal case, for the perfect gas and for the ideal gas, we know there is no interaction is involved, right? So gas molecules are moving very freely. So there is no interatomic potential is exist. But for real gases, where we are treating the gas molecules like they have some kind of interaction between them, so there should be a interatomic potential involved in if we deal with real gases, not ideal gases that we have done the whole derivation right now. For the real gases, so for the real gases, you have to consider this interatomic potential. So apart from the kinetic energy for the real gases, there will be also contribution from the potential energy because of the interatomic attractive or repulsive forces involved, right? So let me write the whole thing. So for ideal gas, there is no interatomic potential, but for the real gas, there exists an interatomic potential. So that means for this case, for the real gas case, for the ideal gas case, the total energy has only contribution for the comes from the kinetic energy. But for the real gas, the E total is dependent on kinetic energy as well as the potential energy that comes due to the repulsion or attraction between the gas molecules, as there are interatomic potentials are involved. So, so that means for this kind of a real gas, the equation of motion would change. That is definitely, we know, for ideal gas, uh, we know the virial equation of state, right? So for ideal gas, we have to use this virial equation of state where PV by RT equal to A 1 to 1 plus B by B plus C by B square plus D by BQ and so on. So as you can see, this A, B, C, so this B, C, D are basically the virial coefficients, okay. Second virial coefficients, third virial coefficients, fourth virial coefficients, so like that. So for an ideal gas, we have to basically, depending upon whatever the potential we are dealing with, we have to calculate this virial, the expression of the virial coefficients, and after doing that, we have to substitute here into this equation of state. By doing that, so we will be getting the equation of state for the ideal gas. Okay. Okay. So let just do it. Okay. So as we know, for real gas, of molecules individual molecule interactions are present. Okay. So that means the canonical partition functions basically has basically factorizes into two parts. Okay. So thus in real gas, the canonical partition function Z has two parts. One is arising due to the kinetic energy. Another one arises. That's similar for real gases. Just like real gas. Sorry, just like ideal gas. This term would be similar. And apart from that kinetic energy, there is also a potential energy. So because of the potential energy, we are using a different term called the a factor that is known as the configuration integral. Configurational integral, and its notation is given by the small z. Okay, and this small z basically depends on intermolecular potential that we are talking about. Okay, so we have to evaluate this z. Okay, so the thing is, so the partition function, the partition function q, uh, that is the ensemble partition function q, is related to the configuration and entropy by z by lambda to the power 3n. Okay. Now So for perfect gas or for ideal gas, this expression of z, this configurational integral value is given by b to the power n by n factorial. Okay, now if you substitute this here, then this gives you q equal to b to the power n by n factorial into lambda 3n. Now it looks like the 1 by n factorial into b by lambda q to the power n. Q is basically written by 1 by n factorial. B by lambda cube is written by the q, the small partition function, the molecular partition of q, q to the power n. So q to the power n by n factorial. This is the expression of the capital Q. Okay, so by doing this, by taking z equal to v to the power n by n factorial, basically gives you the partition function equal to the translational partition function, right? That it should give, that is like also correct, right? For ideal gas, we know the partition function is only gives you the translational part, and that is true here also. Okay. So anyway, so now this is for the case of ideal gas. Now for real gas, there is a interatomic potential is involved, right? So for for a real gas, this z, this integral z is basically given by 1 by n factorial. The integration would be 1 e to the power minus beta bn into dr1 dr2 dot dr. If the n numbers of particles are there, okay. Uh, this Vn is basically uh, the potential energy due to the interaction of all particles. Okay. This is given by this quantity Vn, the interaction. For perfect gas, we know Vn is equal to 0. For ideal gas, that basically ends up with 1 by n factorial, the whole dr1, dr2, drn. If you do the derivative, this gives you the volume, the whole volume of the container by n factorial. That we have just v to the power n, so v to the power n by n factorial, that we just have calculated. Right? Okay. Now, now let's take a pair potential kind of a potential. Okay. So, so for a time being, consider consider the pairwise interaction. Okay. If you consider the pairwise of interaction, let's denote z as z2 equal to 1 by 2 factorial the whole integration to the power minus b2 by pt dr1 dr2. Okay, now here, so here what we have done, uh, so if you know the z value from here, you can calculate the value of b to the virial coefficients b. Okay, that relation is given by b equal to na by v f into dr1 dr2, where f equal to e to the minus v2 by kt minus 1. This f is basically known as the Mayer f function. So this is basically a like for the time being, like for the sake of this course. So this how this expression, how this b is related with f, how this expression is basically coming, is not our interest, but this result is very important. This one, how the virial coefficients is related, the relation itself is very important. So what we do, we first have calculated and checked what is the expression of this configurational uh, integral. It looks like for the case of a pair potential, and next we are going to be used uh, the Mayer function f in order to evaluate the second virial coefficient, that is b. So how we do that? So for that, uh, let's rewrite this expression b, which will be looking like this: minus 2 pi into na f r square dr. Okay. Here you know f is equal to v2 by kt. Now, uh, now from simply this expression, whatever the expression of the potential, the pair potential v2 is appropriate for your system, you can just numerically calculate this integral for that type of potential, and by doing that, so we will be getting the expression of b, the expression of the virial coefficient. So for the time being, let's consider a potential that is known as the hard sphere potential, where the potential, like the idea of this hard sphere potential is like this. So let's suppose these two are the hard spheres. Okay, so the minimum distance the spheres can come close to each other is their total diameter. Okay, so this is the radius, not diameter, the radius, sigma. Okay, so this is the maximum distance these two spheres can come close to each other, and if their distance between the centers, that's denoted it by r. So um, when r is basically greater than sigma, that is their radius, in that case the potential is simply 0. So nothing is there. Nothing is basically repelling between the spheres. Now, if the two spheres try to overlap by a distance which is lesser than their radius, for that case, for r less than sigma, the V2 would take the value infinity. So this basically ensures that the potential is very strong potential which cannot basically allow these two spheres to like move throughout their centers. Okay. Now, so just we will put this condition. This is basically how the potential looks like. We just put this expression of the potential into this Maillard function here, and because since that is required in order to get the value of B, so for r less than sigma, less than equal to sigma, we told V2 equal to infinite, so that means e to the power beta V2 gives you 0, so f gives you -1, because 0 minus 1 gives you -1. Now r is if greater than sigma, in that case the potential would be very small, 0 almost. So e to the power beta V2 gives you 1, so f gives you 0. So for the first case where r is less than sigma, the f equal to -1, and if r is greater than sigma, the f equal to 0. So after getting that, let me just put all the things together. So beta gives you B gives you the virial coefficient. B gives you 2 pi Na into 0 to sigma r square dr. Okay. And for sigma to infinite, that is 0 into r square dr, right? So this gives you 0. So only 0 to sigma is possible. So 2 pi Na into sigma cube by 3 to 2 by 3 pi Na into sigma cube. Okay. So that would be the expression of the second virial coefficient B looks like. For the case of pairwise interaction between two particles, two rod heart shaped, two basically hard interacting spheres. Okay, so what we basically did, we started like for a real gas, we started from its expression, how its expression looks like. So what makes the real gas separate from an ideal gas? Because the real gas has interatomic potentials, right? So basically the molecules inside the gas, they are basically facing the interaction and repulsion because of this potential. And apart from that potential, there is also the contribution from the kinetic energy is there. So the part for the real gas, this total energy is dependent upon both the kinetic energy and the configuration integral. So this configuration integral basically accounts the potential, the interatomic potential term. Okay. So this is how for a real gas this configuration integral looks like. This Vn is basically that form of the interatomic potential. Now for an ideal gas, okay, so for ideal gas, this potential is 0 as there is no interatomic potential. So putting Vn equal to 0 into the expression gives you Z equal to V to the power n by n factorial, and if you substitute simply this into the expression of the ensemble partition function, that basically gives you the old old function for the translational partition function that is true only for real gases, sorry, for the ideal gases. Now if you consider a pairwise potential where two particles, one and only two particles will be interacting with each other, one and the particles which are in closer vicinity with each other, those two particles will interact. And if we consider such type of interactive pairwise interactive potential, so for that case the configuration and integral Z2 will take this kind of a form, where V2 is the functional form of that pairwise interacting potential. dr1 and dr2 are basically the position of the two particles. So here in order to calculate the V, because we want to know for this kind of a system what would be the equation of state looks like. So for that we first have to calculate the second virial coefficient. The expression of the second virial coefficients are given by this, where f is known as the Meyer f function. Now what we did here, we consider a potential which is known as this uh, hard sphere potential. So let me write it like right here. So this is known as hard sphere potential. So hard sphere potential means when the center of two hard spheres were distance much more than their radius, then the potential is simply equal to zero. Like here you can see. Okay. Now if when the particles overlap distance is less than sigma their radius, in that case the potential becomes infinite. So that basically ensures that they cannot basically overlap beyond their centers. So just this is kind of a step kind of a function for a potential. So what we did is substitute for two different distances greater than and less than equal to sigma, and we got the values of this Meyer function. So for r less than equal to sigma we get f equal to -1, and for r greater than sigma we got f equal to 0. So for these two limits we have basically substitute into this expression of the virial coefficient b, and after doing that we are getting this expression of b equal to 2 pi by na sigma 3 by 3, or 2 by 3 pi na into sigma. This is basically the expression of the sigma, expression of the b, the second virial coefficient. So if you put this value into the equation of state, so this basically in that case the state equation of state gives thermodynamic property for your system. Okay. Now we will start our discussion on Bose-Einstein statistics, and after that we will also discuss the formulae of statistics. Okay. Previous discussions, the classical particles discussion, like a classical statistical mechanics discussion that we have done is uh, mostly for the case where the particles are like classical particles. So the Boltzmann distribution that we have discussed, where we treated the particles as a classical particles, and so there what we have basically assumed that in an energy state, basically any numbers of particles can occupy, right? There is no upper restriction for a particle for a state to occupy, right? That is one assumption that we have considered. Next is the particles should be distinguishable particles, as they are classical particles, but they are basically distinguishable particles, right? So that is basically two kind of a assumption that we have considered for Maxwell-Boltzmann distribution. Now comes the quantum particles, okay, like the bosons, fermions, electrons. Electrons, protons are from basically at the fermions here, and boson means the photons, phonons. So these are the basically bosonic particles. Okay. So in this quantum particle system, there are basically rules of the occupancy of a particle. So there's a basically occupancy rule is exist for like for quantum particles. Similarly, for quantum particles, as they are very small scale, so they are basically indistinguishable. You cannot basically distinguish between those two particles. This is a very significant difference compared to its classical counterparts. Okay. Uh, Let me first discuss what do you mean by Bose-Einstein statistics. So before doing uh, before going into the Bose-Einstein statistics, let me just briefly discuss about the Maxwell-Boltzmann statistics. So in MB stat, the microstates, the number of microstates is basically how differ. So under a macro state, the number of microstates are basically coming from how differently each like the how differently the micro that particular microstate, sorry, that particular macrostate can be arranged. So that number of the number of possible configuration, uh, the number of permutation and possible configuration for a macro states basically gives you the number of microstates. Okay, the combination of a given macro states basically gives you the number of microstates. Okay. given macrostate. It's like this. So let's suppose there are four compartments are there. Sorry, four particles are there. A, B, C, D, right? And two compartments are there. So let's take a microstate, sorry, a macrostate where three particles there, as there are two boxes are there. So let's consider macrostate where three particle would be in box 1 and two particle would be in box 2. Sorry, one particle would be in box 2, right? The number of ways this kind of configuration is can be happen basically gives you the number of microstates. This is how the different types of configuration can happen. It can be B, C, D, A, it can be C, D, A, B, can be, so like this, that can be A, B, C, D, there can be D, A, B, C. These are the four possible configuration can happen under this macro state. So that means there are total number of microstates are four. Four is the number of microstates is basically 4, right? So the W would be also 4 here for this problem. So this is how the classical Boltzmann statistics looks like. Okay. Now for the Boltzmann-Einstein statistics or the B statistics, we know the particles are basically indistinguishable. So you cannot basically distinguish between these two particles, unlike the case of Maxwell-Boltzmann distribution, where each particles are distinguishable. Here you cannot able to distinguish. So in that case, for B stats, for B stat, the particles cannot be distinguishable. For this kind of indistinguishable particles, what can happen? So there's only one configuration is there, right? So either like any three of the particles, since all the three particles have similar identical basically. So you can do it like this instead of ABS. You can use dots. So only this configuration is possible. Other combinations are meaningless since all the particles are basically identical. So this is the only configuration that is happening. So now here the three particles can be kept into one box. The reason is here we are not imposing the Pauli's principle. So for bosonic particles, this Pauli's exclusion principle does not apply basically. So that means for a particular states, there are more than one particles can occupy. Okay, which is happening here for Bose-Einstein. So let me write it. Okay. So each of the energy state can accommodate more than one particles. Now next thing is so this is basically the main crux of the Boltzmann-Einstein history statistics. Now what we will be doing next is so this is for this configuration. What we will do, we will basically further divide each of the boxes into four different compartments. Okay, so like the boxes are like these boxes are divided into four compartments like this one and this one. There are, so if there are components like this, then that means each box there are many other configuration that can happen like this. The three particles are here, or it can be like this, where two particles are here, one particle is here, or it can be like this. Three particles are distributed. So many kinds of possibility are, will happen. But for one particle, there are only four, either here, either here, either here, or either here. So these are basically only four possibility is exist for the single particle. But for this three particle, there are multiple configuration exist. So how to calculate? Okay, so here um, for the first case where three particles are there are total 20 different ways of arranging three particles in four four component box. Okay. In contrast, for the second one, only four defined ways are possible. Right. So, so for a bosonic system, in general, the number of ways W1 into W2 20 into 4 is 80% usable. Okay, so let's now take an example where we actually able to want to calculate if there are n numbers of cells are there, and n numbers of g numbers of cells are there, and n numbers of particles are there. How can basically those particles are distributed in this g numbers of cells, uh, uh, in by considering the fact that all the particles are basically bosonic particles. Okay, so, so each cell, let's take each cell numbered 1, 2, 3 like that up to g, as there are g numbers of cells are there, and phase points, let's denote the phase points of the particles at a b c d, although all this a b c d are dis, uh, indistinguishable, since they are the bosonic particles. Okay, so particles are lettered as a b c up to n, and they're indistinguishable. Okay. So what we can do, these are basically the energy boxes. So each of the particle boxes, let's label it 1, 2, 3, and the particles can distribute like this: 1 AB, 2 C, there is maybe nothing, 4 D, E, F, so like this. So this is a basically a particular sequence by which the particles can distribute it. So each of the um, each of the sequence basically gives you a microstate. Okay, this is a basically a microstate. This way there can be other microstates can be added. Like this is one microstate. Similarly, there can be other microstate like this: 1 into D, G, 2 so nothing, 3 into AC, 4 into F, B, FB. So this is also a different configuration. So likewise, each of these possible sequences or configurations are basically known as the microstates. Okay. So if there are g numbers of cells are there, so there are g ways in which a sequence can begin, one of each g. So each sequence can start with a particular number 1 to 3. So as there are g types of numbers, so there will be g numbers of ways, right, by which the sequence can start basically, and the remaining g plus ni minus 1 numbers and letters can be arranged in any order. Okay. So the remaining ones are g plus n minus 1, ni minus 1 are the numbers and remaining numbers and letters. So these numbers and letters are basically arranged later. So we also have to consider the numbers of ways in which those numbers and letters can be arranged, right? So we have to consider both the facts. Okay. Sequence can start and remaining so numbers of where the sequence can begin equal to g into g plus ni minus 1 factorial. Okay. This is the possible way the sequence can begin. Uh, so so for each state, ith state, the total number of microstates. So for ith state, the total number of microstate is basically given as wi equal to g into g plus ni minus 1 factorial into g factorial ni factorial, which gives you g plus ni minus 1 factorial divided by g minus 1 factorial ni factorial. Now from here, the example that we have done, we are doing it basically. So there are numbers of particles was 3 and g is the compartment, that was 3, that was 4 actually. You have divided the box into 4 compartments. If you substitute this thing here, the number of ways basically gives you 4 plus 3 minus 1 factorial divided by 3 factorial by 3 factorial. So 4 into 3 factorial by 3 factorial gives you 4. Sorry, this is not. This gives you 6 into 5 into 4 into 3 factorial by 3 factorial by 2 factorial. Which 26 is 5 into 4 equal to 20. Okay. Now, since we got the configuration here W, uh, from here actually we can, so the way we have calculated the Boltzmann distribution, the same process we can use here also. So the total for each of the box there would be some configuration W. So the total W would be the multiplication of all W's. So this gives you the multiplication of G plus I minus 1 factorial, G minus 1 factorial into I factorial. Now we have to find out the distribution of particles which would maximize this W thing. So for that we first take the logarithm on both sides. That makes the multiplication into summation of ln of G plus I minus 1 factorial minus ln of G minus 1 factorial minus ln of I factorial. Now if you do this, it will give you ln W equal to summation over Ni plus G ln of Ni plus G minus G into ln G Ni into ln of Ni. Now if you take the derivative, because the derivative terms should have equal to become 0. Derivative of ln W if you take, this gives you summation over ln of G into Ni 0, Ni 0, G Ni equal to 0. Now, so this we basically we will now do this Lagrange method of undetermined multiplier. So for that we need constraint, and we know there are two constraints that is already there in the system. The first constraint is on the energy. The first constraint is on the number of particles. So the total number of particles is fixed. Ni is fixed, some constant. So you can write the derivative of dni summation over I equal to 0. Similarly, total energy is also fixed. Ei Ni summation over I equal to some fixed constant. If you do the derivative here also, Ei into dni summation is equal to 0. These are the two constraints. So now we will impose the constraints into this equation. After doing that, we'll be getting summation over ln of G into Ni 0 into Ni 0 minus. So these two types of constraint we have to follow. The first constraint, so the alpha is into Tni. Second constraint getting beta as epsilon I Dni equal to 0. Now we are taking alpha equal to ln b and beta we are simply taking as beta. Okay. So that gives you this. We are doing just to make the calculation simpler. Okay. So Ni 0 minus ln b minus beta ei if you take dni as common. Now dni cannot be so the dni cannot be equal to 0. So only thing that can be equal to 0 is this one. So that means ln of g into plus ni 0 plus ni 0 equal to ln b plus beta here. So now from here ni 0 by g equal to 1 by b beta ei minus 1. Okay. So for our energy state ei, this should be the way how the bosonic particles will be distributed. Okay. This is different from the case of Maxwell-Boltzmann distribution, right? So this is the distribution for these. Particles. And this is called the B statistics. Okay. Now comes the Maxwell-Boltzmann statistics. Uh, so for case of Maxwell-Boltzmann statistics, the thing is, so things are becoming a bit different. So here particles basically obey this Pauli's exclusion principle. So for a particular energy state, they cannot occupy more than one particles. Okay. So here also particles are indistinguishable. Next thing is Pauli exclusion principle applies monoton particles in the same energy level. Okay. So that means, so if you take our similar example, previous example, two boxes are there, three particles in box 1 and single particle in box 2. So for this three particle in box 1, if we divided the box into 4 compartments, this whole thing looks like this. Now the thing is, there are only one component, one particle is only possible. One component cannot contain more than one particle. So that means possible configuration looks like this. Second configuration would be this. Third configuration would be this, and fourth configuration would be this, and this. So these are only 4 configuration happen. Similarly here also 1, 2, 3, 4. 4 configuration. 4 here also, 4 here also. And total configuration W equal to 4 into 4 equal to 16. Okay. So that means, so the total weight, the weight would be simply, the weight is W. For a general expression, let's suppose n particles are there and g numbers of compartments are there. So for that kind of a case, so g compartments at ni number of particles. So for that case, the weightage would be Wi would be simply g factorial divided by n factorial into g minus ni factorial. This is the case for the Maxwell-Boltzmann distribution. Okay. Yeah. If you can check it here for this problem also, if you put the value g equal to 4 and n equal to 3, you will be getting Wi equal to 4 for the previous above problem. Similarly, here also one can calculate the distribution for which this configuration W can be maximized. For that, so the recipe is same. So first, what you have to do, you have to take the log on both sides. Log W equal to summation. The multiplication is converted into summation of g into ln g minus ni ln ni minus g into ln g minus ni plus ni into ln g minus ni. Right. Now, in the case of the maximum, you have to take the d derivative ln w to summation over ln g minus ni 0 by ni 0 d ni equal to 0. Similar way, here we have to put the constraints. The constraints are here singular t ni equal to 0 and summation over understood over I bi d ni equal to 0. So the similar way, these two constraints have to be kept into this equation, and after doing that, so the distribution kind of gives this kind of a distribution you'll be getting ni 0 by g equal to 1 by b to the power beta b to the power beta here plus 1. Okay. So this would be the distribution for the Fermi-Dirac case. How the distribution looks like, that would gives you the maximum configuration. Okay. So the distribution for three different types of statistics looks like this. So different distributions looks like this. So for MB, distribution of particles at energy state I, E, I looks like this, e to the power beta EI. For FD, distribution Ni looks like this, 1 by e to the power EI by e to the power minus beta EI plus 1 for NB, for FD, and last for BE, distribution looks like this, Ni equal to 1 by e to the power beta EI minus 1. So these are the three different types of distributions. Now for FDBE is mainly applicable for quantum systems. Now for very high temperature or very high low density, where the particles like the indistinguishable conditions basically vanishes, the particles become distinguishable. So in classical limits, that means that high temperature or low density. So this eta b to the power e basically becomes much higher than 1 or 2. So both this FD and B stats converge into the MB stat, okay, where the distribution is given by Ni equal to e to the power minus beta EI. So this is the classical limit where the temperature is very high or the density is very low. Either of the cases, the particles, the indistinguishability condition for the particles basically vanishes. The particles become distinguishable. So that means the particles basically behaves classically, which turns the both these two statistics into the classical MD statistics. So now let's do a problem regarding this. Okay. Okay. So the thing is, problem is compare the distribution for three types of statistics. And thing is, the number of particle n is 3 and the g equal to 2 are the particles, and this is the energy states. Okay. So there are two states, state A and state B. The number of particles are 3. Okay. So for the classical case, let's for as these particles are basically classical particles, so that means these are basically distinguishable particles. You can distinguish among the particles. So let's number the particles as 1, 2, and 3. So state A and state B, two states are possible. State A has So for classical particles, let me write all the possible configurations. So first case is all the particles are in state A, no particles in state B, 1, 2 particles in state A, third particle is B, 1, 3 is in A, 2 is in B, 2, 3 is in A, 1 is at B, now the opposite, 1 is at A, 2, 3 is at B, 2 is at A, 1, 3 is at B, 3 is at A, 1, 2 is B, nothing at A, 1, 2, 3, both are in B. So these are the all the combinations that can be possible by considering the particles are classical and distinguishable, and each of the states can accommodate any numbers of particles. So the total number of distribution configuration 1, 2, 3, 4, 5, 6, 7, 8. Total number of distributions are basically 8. So this also can be calculated from a formula. So the configuration formula is basically g to the power n. The number of states are g, so 2 to the power n is the number of particles 3, that gives you 8, which is here also getting 8. Okay, so it's kind of consistent, this formula. So this is for the case of MB. Okay, MB. Now comes the B statistics. So for B statistics, for the B statistics, um, so there are two energy states are there. One is the state A and B. So in A, so in B, in A, maybe there are 3 particles are in A and no particles in B. As all the particles are basically indistinguishable, so you cannot able to cannot able to mark which particle is there as they're identical. So 3 particles can be in A, 2 particles can be in A, 1 particle can be in B, 1 particle can be in A, 2 particle can be in B, no particle in A, 3 particles can be in B. These are the 4 combinations that can happen for the case of B statistics, right? Uh, the thing is, for B statistics, there is also formula, right? So the formula is basically this. This is the formula. What is this? This one. This one is the formula. Okay, we can use this formula here actually in our problem also to check whether the thing is correct or not. So the formula looks like this: the number of distribution uh, Z, or is given by n plus g minus 1 factorial by g minus 1 factorial. If you do it, gives you 3 plus 2 minus 1 factorial by 2 minus 1 factorial. So 4 by 1, that gives us 4. there is also g minus 1 factorial into n factorial. G minus 1 factorial into n factorial. We do it. G minus 1 means g is here 2 minus 1 factorial into number of particles 3 factorial. So 4 factorial by 3 factorial, this gives you 4. Now it's fine. Okay. So by using this relation also, distribution relation also, you can verify the same result. Lastly comes the FD statistics, the Fermi-Dirac statistics. So for the FD statistics, we have only 3 particles and 2 states, right? So it's not possible actually, because there are 2 states and 3 particles there, so we have to accommodate 2 particles in one state, which is not allowed in case of Fermi-Dirac statistics. It's only possible, so 3 particles in 2 states is not fine, or is not possible. Only 2 particles in 2 states can happen, or 3 particles in 3 states can happen. So if that is the case, 2 particles in 2 states, in that case the configuration Z also is given by here, the same formula for FD stats. This gives by, what is for FD stat, g factorial into n factorial by g minus n. So g factorial by n factorial, g minus n factorial. Okay, so g is 2 factorial by 2 factorial into minus plus 0 factorial is 1. 2 factorial by 2 factorial is 1. So one possible combination is only there, but these are the 2 states and these are the 2 particles. That is only configuration that can happen for every test. Okay. So we have discussed like for different types of cases. These are basically the 4 different types of statistics or distribution that can happen. Now, if there are 3 particles, 2 configurations are there. How for different statistics, how the particles are distributed. First, we have discussed the Boltzmann or classical distribution, where 3 distinct particles are basically distributed in 2 states, and where each of the states can occupy any numbers of particles, and particles are distinguishable. So we have marked the particles as 1, 2, 3, and we got the most distribution, the 8 possible distribution, the most among all the 3. Next is the B stat, where although the particles are indistinguishable, but still each of the state can accommodate any numbers of particles. And here we got 4 types of distribution. And lastly, for the FD stats, which basically includes the Pauli's exclusion principle, that results into that one energy states cannot occupy more than 1 particles. So by that logic, it is not possible to basically occupy 3 particles in 2 states. Only it's possible either 3 particle 3 states or 2 particle 2 states. And by considering that fact also, the one possible configuration is there only, and that is 2 particles in 2 states. This is the configuration. So now let me complete the class for today.